Thanks, Paula, for the kind introduction, and thanks, Kameka, for the opportunity to speak today. And as Paula mentioned, I'm Ping. My background's in silicon PV, but I also dabble a bit in uh, tandem devices. Before I begin, I should probably emphasize that a lot of the work presented here, the results are the work of my colleague, Miss Jiali Wang. I think she's in the participants here as well. Yes. So a brief introduction about the ANU and particularly PV R&D research, R&D at the ANU. I'm not sure if everyone knows what the ANU stands for. That's the Australian National University. We are located in Canberra, so we are about somewhere between Sydney and Melbourne. The solar energy research at ANU has a history of about more than 50 years, and including about 30 years of it focusing on silicon PV research. Currently, we have about 50 staff and students in the group, and about half of it working on silicon, half on perovskite. Research activities at the ANU covers silicon materials, so that's the defects in silicon wafers. We also research passivating contacts, both high and low temperature, characterization, particularly focusing on photoluminescence and electroluminescence of devices, perovskite solar cells, and of course, tandem devices, and also on module U and modeling and of sorts. So the photo on the bottom right here, this is of the University Avenue. This is just in front of the engineering building where our lab is located. Cool. Now that I got that out of the way, a bit of background, a bit of outline of the talk. We'll start with some background on solar PV, and then a brief review of applications of SIMS in solar PV, a study into inkjet printing, and also this application of SIMS to identify the localized doping of the inkjet printing. Great. So why solar PV? And the motivation for myself has remained the same for the past 10 years, and that is really to fight climate change. This figure here is from the recent synthesis report from the IPCC from this year, and basically it summarizes that climate change is already here. The last decade is already 1.1 degrees warmer compared to the pre-industrial era. And it says here that this has led to widespread adverse impacts and related losses and damages to nature and people. So it is very much already here. I think we are all already experiencing it. But what the world will look like in the future, that depends a lot on what we do now. And there's a lot that we can do to make sure that we avoid the worst possible scenario. So to minimize the impact of climate change, we have an urgent need to reduce greenhouse gas emissions. This is a plot of the expected, the net greenhouse gas emissions and annually as a function and the trajectory for the temperature rise. So if you want to have a chance of limiting the temperature rise to about 1.5 degrees, we have to peak in the global emissions has to peak very soon. And in about 2030, we have to drop by almost half of the global emissions at 2019. So that's 7 years left. So that's not a lot of time. And it's roughly accepted that to limit it to 1.5 degrees, we need to reach approximately net zero emissions by 2050. So we don't have a lot of time. So, but there are a lot of options, mitigation options for avoiding this, the damage that comes with it. This graph here shows this image figure here shows the mitigation options across different sectors, including the cost. So on the bottom right here, there's a legend for it. So blue means the costs are lower than the reference, and red means the cost is very, very high. If you look at the entire figure here, we see that at the very top row, solar and indeed wind combined together has the highest potential for mitigations. And if we zoom in on the figure here, over here, I'm not sure if you can, hopefully you can see it clearly. A large portion, significant portion of solar and wind are in the blue region, which means that the costs are lower than reference. So that means that the solar and wind combined has one of the strongest potential for mitigating climate change, and it also is a very cost-effective option overall. And this is particularly focusing on up to 2030. If you look into slightly longer term, this is from the IEA World Energy Outlook report from last year. For under the net zero emission scenario, we also expect the growth of solar wind to grow. It's over here. I think it's this orange one, and it's going to continuously grow. And it's a bit smaller than doesn't look like a lot, but in this scenario, this is total energy use, so it's not just electricity. But wind and solar is combined is expected to contribute to more than 70% of the electric supply. There are also other models who suggest that the numbers would be higher. So one of the reasons why solar has been so cost effective is demonstrated here in this figure here. This shows the average module sales price. This is commercial sales price as a function of the cumulative module shipment since the 1976. Each dot here represents a figure from one year. Can see that the cost of the modules has decreased significantly over time. Since 1976, the price has decreased by almost $3 a magnitude. Not yet, but I think I'm confident we'll reach that number. And the breakdown of the cost improvement can be attributed to two main components. So that's the one in the gray, efficiency learning, contributing to about 8%, and the per piece learning, that's a production cost reduction of about 15%. Combined, it means that every doubling of the cumulative shipment, the price reduces by about 25%. So what this graph highlights is that if you want to further decrease the cost of PV, and there are a lot of incentives to do so, to make it cheaper and make it more widespread, we need to reduce consider not only efficiency of the devices, but also the production cost of it. So focusing on the efficiency of solar PV, this graph here, it highlights a trend. It's almost like a Moore's law of the solar PV in the last 10 years. I know the history is much shorter. But approximately the average cell conversion efficiency, so that's the power output of the cell, increases by about 0.6% absolute annually. Not sure if it's an effect of a self-fulfilling prophecy or self-fulfilling KPI of sorts, but it has been kept to quite successfully. But although this trend has been quite steady, the improvement efficiency has actually been gone through a few cycles, from the very, very early cell structure based on aluminum BSF, transition to PERC, when the efficiency of the aluminum BSF has reached its maximum, around 20%. And then now we are heading towards the end of the PERC cycle. PERC is dominant cell technology right now. We're heading towards passivating contacts over the next few years. And part of the improvement efficiency, in addition to cell architecture, of course, is also better understanding and improvement of the cell and module technology that's involved, every part of it. So I've mentioned passivating contacts here previously, and this is a big part of the talk as well. We'll mainly be focusing on polysilicon passivating contacts. It's sometimes also known as TOPCon or POLO. Essentially what it is, if you look at the TM image here, we have a layer of polysilicon at the bottom here, sorry. This is heavily doped typically, up to about, say, 1E20 to about 3E20 in that range. And this polysilicon sits on top of a very thin oxide, typically about 1.5 to 2 nanometers oxide. And then it provides, by having that interfacial oxide separating between the crystalline silicon and polysilicon, allows this structure provides both surface passivation and good electrical contact, typically through tunneling effects, either that or pinholes in the oxide. So the figure on the left here, this shows a typical cell structure of the so-called TOPCon cell. This is the dominant, or will be the dominant cell structure in the next 10 years. Essentially, it's an N-type silicon wafer with a boron diffusion on the front. And the rear surface is where we apply the TOPCon layer, so the oxide and then the N+ polysilicon layer. The polysilicon layer is amazing. It's one of the lowest recombination sites right now within the cell, but unfortunately, it is still limited to the rear surface due to the absorption, the unintended parasitic absorption of the polysilicon if you place it on the front surface. This graph here is from the ITRPV, so that's the International Technology Roadmap for Photovoltaics, a conglomerate of a group, of PV industries and researchers. And this shows the expected trend or the world market share of different cell technologies. What we want to focus on here is a TOPCon on N-type mono. That's the one in gray. Currently, it's about 10%, but in about 10 years' time, it's going to grow to about 60% of the market share. And some analysts are saying that this number will be higher as well. And this rapid transition, as we've shown earlier, is generally this pursuit of higher cell efficiency, and also that this technology is quite compatible with the current incumbent technology of PERC. So that's the rough background of PV and polysilicon. Next, we'll move on to the applications of SIMS in PV, which I think has had significant role to play in improving not just efficiency, but also the reliability of silicon PV and PV in general. I'll go through some examples here. The first one is work from my colleague Di Kang, studying on the effect of hydrogen content at the interface of the polysilicon. So if you look at this SIMS image here, it's the silicon oxide interface is roughly around 70 nanometers, and the concentration of hydrogen in this region, if it's integrated and plotted as an x-axis, and compare that with the J0, so that's a measure of the surface recombination. So the higher it is, the worse it is. We see that there's an optimal trend. There's a trend that shows an optimum in the middle here. If there's not enough hydrogen, there's not enough passivation of the dangling bonds. If there's too much hydrogen, hydrogen itself starts to become a recombination center and starts to become a problem. So if you're interested in it, you can find out more about it. And I think it's still on the Kameka Learning Zone, one of the webinars delivered by my colleague Di Kang. We've also used SIMS to, I think this is quite commonly used, comparison of SIMS and ECV measurements to look at active and inactive dopants. In this case, we've used it to look at to understand the limiting factors in boron gallium co-doping of P+ polysilicon. In this case, with this is a work from my colleague Tian. In this case, we'll focus on this. If we just focus on this image on the bottom, on the right hand side here, this is a comparison of the SIMS in the solid line, and then the dashed lines, that's the ECV, so that's the electrically active dopant of gallium doping. And we see that with gallium doping, we get really, really good passivation, but we can't get good contact. And that's normally understood as because gallium doesn't provide solubility limit of gallium is not as high, doesn't provide that level of concentration that is needed to form good contact, electrical contact. But if we look at the SIMS here, we see that the actual physical concentration of gallium is actually much higher. It means that there's actually a lot of gallium, and indeed, this inactive gallium other groups has used this inactive gallium and managed to activate them using pulse lasers to achieve good contact with gallium doping. Next, we also use SIMS to study the scattering mechanisms of polysilicon. On the left here, we have a phosphorus dope, N-type polysilicon. On the right, it's a boron dope, P+ polysilicon. We have two samples here. One is intentionally contaminated with iron. One is a control, which is a float zone clean wafers. And by comparing the two, we can identify where the iron is concentrated. And we see that in the phosphorus dope polysilicon, most of the iron is concentrated within the polysilicon layer. But if you look at the boron dope polysilicon, we see that most of the iron is actually concentrated in a surface layer above the boron polysilicon, typically known as the boron-rich layer. So that's an example of the applications. And another one, this is a bit older reference, but mainly focusing on multicrystalline silicon, but SIMS can also be used to identify contamination species in silicon wafers. Typically, this is quite difficult because the concentration of impurities in silicon is typically within the bulk is typically too low to below the detection limit of SIMS because they don't need a lot of metal impurities to severely affect the lifetime of a sample. But if we do a gathering, so in this case, doing a phosphorus diffusion, we can concentrate most of the iron metal impurities, into the front surface and allows it to be extracted from SIMS or measured on SIMS. In this case, it reveals that a lot of the metal impurities are chromium and iron. In comparison, if we've already run the same process on a sample that has already been gathered, we don't see a lot of chromium and iron. This also shows that gathering is very effective at removing chromium. Next is studying the degradation of modules that incorporate electroplated, electroplated copper fingers. This is a big area of research right now, working on trying to reduce silver consumption and to replacing silver by copper. These images here show ER images here show that the degradation in a damp heat test very localized. The authors from I think it's Arizona State University managed to identify how the copper were transferred from the contact regions, the fingers, the metal fingers, into the non-contacted regions between the fingers. And using SIMS, they showed that the copper has actually diffused through the EVAA encapsulation. So it basically goes to the encapsulation layer and then goes sideways into the non-copper area and back into the silicon wafer. And so that's a good indication, a good study, a good app used to identify degradation pathways. Next, it's also been used to study a well-known degradation for PV panel in operation in PV farms called potential induced degradation. This is when solar panels are connected in series, resulting in voltages of a few thousand or few thousand volts compared relative to the ground. And this high voltage induces the diffusion, the migration of charged ions such as sodium. In this case, when they compare the sodium concentration in shunted and non-shunted areas, they find that the shunted areas show significantly higher concentration of sodium. And this allows the targeted barrier layers that it's more effective towards sodium. And I think it's pretty much solved at the moment, as far as I understand. And of course, SIMS has also been used to study the degradation mechanisms of perovskite solar cells and also tandem devices. So SIMS is, in short, SIMS is very, very useful to understand the limiting factors, degradation, and pathways to improvement for silicon solar cells and also perovskite solar cells. Next, I'll go through a bit more about what we do, particularly with inkjet printing. So previously, we've mentioned that in the standard TOPCon structure, most of the polysilicon passivating contacts is limited to the rear surface because of absorption of light. So it's less efficient if you apply the polysilicon on both surfaces. But an alternative structure is to basically turn the device into almost a 3D structure by having an alternating between p-type contact and an n-type contact, and then they're typically in the rectangle, and then there's just alternating strips of n-type and p-type and n-type and p-type polysilicon. So indeed, the group at ISFH has demonstrated, I believe it's still the world's highest efficiency of a laboratory cell using a IBC polysilicon solar cell. In the industry, there's also significant interest in demonstrating back contact solar cells with ICO Solar already demonstrated or reported open circuit voltage of about 745 millivolts. This is on in industry, in large area devices. But it is generally accepted that successful commercialization of the technology requires cost-effective processing, and a big part of it is patterning. So here's where we think the inkjet printing can be helpful, can be useful. Inkjet printing essentially allows you to print various materials. In the case of solar cell technology, it has been used to print dopant material. We've done that, and there's various groups that have done that as well. Used to print metal fingers, that has been demonstrated, and also to print masking layers, among others. It has good flexibility as long in terms of what you can be printed. There's a bit of a requirement on the viscosity of the material, but generally that it can be adjusted to fit the applications. And all this means that you can print you can have localized doping. In this case, what we're proposing, without a masking step or without a patterning step. And we'll show later as well, hopefully we can combine the annealing of the boron diffusion and the phosphorus diffusion together, so eliminating one of the high temperature steps for the process. And largely we believe, and next we believe that inkjet printing, there's a lot of interest in it in industry, not just in PV, and we believe that technology will be scalable. Yes. So I'll briefly review the results that we've had. In the figure on the left-hand side here plots the implied VOC, so that's the voltage. The higher the voltage, the better it is, and against the annealing temperature. So on the left, it's boron dope. On the right, it's phosphorus dope. We see that in both cases, we're focused on the hydrogenated case. So this is the hydrogenation is quite commonly done. It's almost built into the cell process and a bit hard to avoid, to be honest. After hydrogenation, we get about 718 millivolts for boron and get about 729 millivolts with phosphorus. So a few things that are useful to note here is that the peak is quite flat around the optimum temperature of around 950. And the other thing is more interesting, I believe, is that the optimum temperature for both boron and phosphorus are around 950 degrees. So which is why we believe that we can actually co-anneal that, but we'll look into that a bit more detail later. Cool. So remembering that the optimum temperature is 950 degrees, these two images here show the ECB measurements of both boron dope and phosphorus dope. Essentially, if the doping is too low, the passivation is generally not as good, particularly for the phosphorus. So if the temperature is too low, the doping is not as good, it's not as high, passivation is bad. But if temperature is too high, then you start breaking down the interface oxide, and then you start introducing Auger recombination within the silicon, the crystalline silicon wafer itself, and then the recombination starts to increase again. So the optimum temperature and doping, optimum temperature here is correlated with the optimum doping of the polysilicon. And this will be important later, where we can show that without any doping, you're basically not going to get any passivation with the polysilicon. We've also measured contact resistivity, another important parameter for solar cells, and we showed that the contact resistivity are below 5 milliohms centimeter square at 950 degrees, both for N-type and so boron dope and phosphorus dope. And we've measured this using the Cox and Stroud method. So that's all about the overall performance of what we have. Next, we focus on how localized the localization of it, and because that is one of the main selling point or one of the main advantages of inkjet printing doping, that hopefully we can actually have patternable, we can form patterns without using a masking step. So the first image here is an optical image of the boron droplets without, when they're not touching, we see that each droplet is about 60 microns. There are some leeway to change this value, making it smaller or larger by changing the viscosity, for example, or the printing voltage. But if we decrease the gap between each of the dots that we print, then we start to see the dots overlap. In this case, we see a boron diffusion line, the boron glass line, and the bottom is a phosphorus line. In both cases, they are about 60 to 70 microns wide. Next, we'll look at the quality, the passivation quality localized. First, we'll look at the PR image of the boron dope lines. In this case, we can see that there's a bit of a scallop surface shape of the lines. This corresponds, this is actually very closely linked to the shapes of this, and it's essentially a feature of an effect of the distance between the dots, the droplets. If you decrease the pitch, the distance between each drops, this tends to decrease. The scalloping effect tends to decrease, as you can see in the phosphorus lines here. So we can see with PR image here, and when we look at the PR image, we're making some assumption here that that only the dope regions will provide passivation. Therefore, if we compare the PR intensity, which is a measure of the surface passivation, we can roughly identify the areas that are passivated and therefore dope against the areas that are not dope. But of course, this is a very indirect measurement. If you use SIMS measurements, in this case, it's done using the Kameka IMS 7F auto using O2 plus as a primary ion. We see this really nice 3D map of the boron distribution within the printed area. And we see a nice, I should probably point out this is not to scale. So the z-axis has been extended quite a lot. But essentially we see that it's quite localized. We can even see a bit of an interface here, where before the oxide the polysilicon is in this solid region at the top here. And we see a bit of doping into the crystalline silicon afterwards. If we analyze this image a bit further, for example, if we plot a cross-section of this image, we get a similar feature here. We see that the oxide interface is around 70 to 80 nanometers, which corresponds to what we expect it to be based on our deposition tech conditions. We see a bit of indiffusion into the crystalline silicon itself. We can look a bit further from the plan view at the top. So this is cutting it roughly about 50 nanometers here. We take a plan view of it. We can also see the scalloping effect that is evident in the micro PR and also in the optical microscope. And if we put all this together and we look at compare the line width, in this case, we measure it using full width half maximum for both the PL and SIMS. We see that there's a good agreement. The SIMS review a much tighter distribution of about 60 microns, but they're all in agreement roughly between 60 to 70 microns, which is which is low enough for a IBC solid cell, which typically will be in the range of each fingers will be in the range of around 200 to 600 microns. Next, we do the same thing for phosphorus. We see that first thing is that the PR shows a much straighter lines, as similar to the optical images here. If we look at the SIMS image, again, it's also a very nice image. We can see this really sharp concentration red line here, showing that the concentration of phosphorus is higher over here. And this corresponds to the oxide interface. And what it suggests is that there's a power of phosphorus just within the polysilicon layer, just before the oxide layers. And this effect has also been reported by other research groups. If we do the same thing, we can plot the cross-section of the image, and we can see the power up here again very clearly, a bit of indiffusion into the crystalline silicon. We do the same thing, a good plan wheel showing a good uniformity in terms of width. And if we plot the cross-section, then we can extract the full width half maximum as well. Again, they're all in a very close range of about 60 to 70 microns. So good agreement between SIMS, PL, and microscope, optical microscope. So that's very comforting to know. So next, we try to apply this technology to co-anneal both boron and phosphorus, noting that both of them has optimum annealing temperature at 950 degrees. We've also adjusted the droplet number of droplets to make the lines intentionally make it a bit wider. This allows us to get closer towards a typical printed lines, typical polysilicon lines in the IBC solar cells. If we just look at the optical microscope, or if we just look at the PR image, we see a nice localized passivation around the boron lines and also within on the phosphorus lines. Comparing the microscope image and the PR images, the full width half maximum is also quite similar. So that's looking promising so far. If we do the same thing, again, apply the same technology using same method as before, looking at the SIMS of the samples, on the boron line, we detect boron, so that's good, we expect that. At the phosphorus lines, we detect phosphorus, that's also good. But I guess some of you already figured this, expected this one, is that if we start measuring phosphorus at the boron line, we also see phosphorus. So this is not good news for us. There's not a lot of phosphorus outside of the printed lines. So it seems like this cross-contamination is limited to the areas where it is actually printed, and it doesn't really affect the areas that are not printed yet. We're not exactly sure what's happening here. This is something that we're still trying to understand. But if you look at the SIMS profile here, this is calibrated concentration. The boron is this about 1E18 line here, while the phosphorus on the boron line is not as high as the phosphorus on the phosphorus lines, but still actually higher than boron lines. So what this suggests is that this boron line is very likely actually compensated by phosphorus, and therefore it's mostly phosphorus dope. This is bad news for us because we want to have one N-type and one P-type lines, but it's not very SIMS. The PR shows that it is effective, but the SIMS clearly show that it's not. We have some issues there. And the main issue is not only that if we all completely compensate, but it's also an issue if those two lines starts touching, and then they will form a PN junction, which basically creates a really, really high recombination area. So these graphs here are from the group at ISFH who made the Polo IBC, the 26.1% IBC. And over here, it plots the gap between the N-type poly and the P-type poly as a function, the recombination current versus the voltage. But essentially, if we compare just at the same voltage at the maximum power point here, we see that when the gap is too small, the recombination current actually becomes very, very large. And you do need a sufficient gap to avoid this recombination effect that will be very, very bad for the cell efficiency. So what can we do? We are exploring some options now, and one of them is including a pre-oxidation, doing a short pre-oxidation just before the 950 degrees activation and new. So this image here this is roughly where our printed image. There's a solid area and then lines, and the areas around it are not printed. Firstly, if we measure, this is a sample that has been annealed without the pre-oxidation. And if we measure the area that has been printed, we get this solid line here, which is quite normal. But if we measure the ECV at the non-printed area, we actually start to detect a signal as well. It's a bit lower, but it is there. It is still there as well. And we think that what's happening, sorry, this is, we think that what's happening is that the boron from the boron glass is diffusing out into the non-printed area. This case, it's for boron doping, but we've also seen similar effects for phosphorus doping as well. And you can see in the PR image too that remembering that when you have doping, it tends to improve the passivation quality of this oxide polysilicon stack, and we get this really blurry image because that's doping everywhere. But if we add a short 750 degrees oxidation just before in situ oxidation just before the 950 degrees nitrogen anneal, we can avoid the unintended doping in the unprinted regions. We do the same process here. We get measure the dopant concentration in the printed area, same as before. But now, if we do the oxidation and we measure the areas outside in the unprinted area, the concentration is actually below the detection limit. So I think this is a promising option for avoiding this cross-doping, but definitely needs a bit more work to verify this. So in conclusion, we've used inkjet printing of dopant glass for maskless patterning for silicon solar cells. We have good passivation and contact as demonstrated using full area printed samples. But the SIMS measurement shows that when we're just printing only boron or we're just printing phosphorus, we get really, really clean lines. There's hardly any contamination or auto-doping outside the printed area. So that's good. We can achieve line width of about 60 to 70 microns. But if we co-anneal a sample with both boron and phosphorus lines, we start seeing a contamination of phosphorus into the boron lines. And that's something that we're still working on. So that's the end of my talk. I'd like to acknowledge the funding from the Australian Renewable Energy Agency and also the ACAP, Australian Centre for Advanced Photovoltaics, and of course the colleagues at the Solar PV Group. Thank you.